Okay, hello and welcome back, everybody. This is the last subsection of the overall section, common rules of integration. We're going to talk about definite integrals, which feels the same as it always does. You find an antiderivative and evaluate at the endpoints. But we're also going to really kind of stress this intuition for combined rules. And by combined, I'm really talking about U substitution and or integration by parts. Because nobody tells us when to use one of them versus the other, and what to choose for our specific functions f and or g. So before I get too much into our first example, I do really want to stress kind of the first step in getting good at integrating, and that's that we have to give ourselves the grace to be incorrect. We're almost certainly going to get some of these wrong on our first try, and on future tries. We might get it wrong 5 times in a row, and we need that perseverance to get through those 5 wrong times and just be content the 6th time maybe getting it right then. It's really a hard thing to do in calculus too, because there are so many choices at our disposal. If we make the wrong one, then we're just kind of stuck. So let's look at this first integral that we'd like to define. It is a definite integral, right? I've got those bounds from 1 to 2, and then I have x times the root of x squared plus 3 plus 3 over 6x minus 1 squared. Now, every time we have something like a plus, there's clearly 2 terms here in my integral, and this is why linearity of integration is important. It says that I can integrate these individually. And in fact, I should. I should try to integrate these individually. Okay, so kind of the first step in this problem is to say it's not actually going to be one integral, it's going to end up being 2 integrals. And I guess an equivalent step, because it's a definite integral, is that these bounds 1 to 2, I can just kind of go ahead and drop them for now, and I'm just going to find an antiderivative using the indefinite integral, and eventually I'm going to send myself to f of 2 minus f of 1 to evaluate the definite integral. So we're not going to worry about the definite integral for now. We're just going to try to find an antiderivative. We're going to try to find 2 antiderivatives, 1 for each piece in my integral. So let's just analyze the first of the 2 antiderivatives, which is x times root x squared plus 3. And every time we see roots, and in fact a lot of times when we see denominators as well, it's kind of to our advantage to rewrite them in terms of powers, because the power rule is the way we're going to integrate it. So we'll rewrite that square root as x squared plus 3 to the 1/2 power, and then it's a little bit clear that we do have a function in parentheses. And so U substitution feels good. Feels good. We do also have this multiplication right in the middle that may make you think maybe we should do integration by parts. Now, I want to comment, this is where I always say it's a good idea to try to do these to one step in your head, both at the same time. If I were doing integration by parts, it's probably to my advantage to take a derivative of that term, right? I would want to take a derivative of x because the derivative of that term would be 1 then, and then my second integral might be easier. Let's jump back to integration by parts. If you take a derivative of one term, you actually have to take an integral of the other term. So if we were using integration by parts, we'd have to try to find the antiderivative of the square root of x squared plus 3, which is not going to be an easy thing to do. So that's kind of my intuition saying integration by parts is probably a bad idea, even though we do have this lovely multiplication right in the middle. We also happen to see that we have a function in parentheses. Moreover, if I go ahead and think really quick, call this function in parentheses g, x squared plus 3, what is its derivative? Which I'm looking for inside of my problem, well, that would just be 2x. Now, 2x is not what I have out front here. I just have a single x, but that's pretty darn close to 2x. So U substitution does feel like a better choice here. And I'm going to choose U being this x squared plus 3 term, in which case du will end up being 2x dx, or if I go through that work of dividing both of these by 2, cancel the 2's on the right, I end up with du over 2 is this x dx, which is inside of here. So that's what I'm going to do. I'm going to replace x squared plus 3 with u, so this will just turn into u to the 1/2. And we'll replace x dx with 1/2 du, so x dx with 1/2 du. And at this stage, the antiderivative of u to the 1/2 times 1/2 du, the 1/2 part can just come along for the ride. So that power, I'm just going to use the power rule on it, right? I'm going to use the power rule on that u term. I'm looking at u to the power 1/2 plus 1, and I'm going to divide by the new power 1/2 plus 1. If I go ahead and simplify that, my denominator turns into 3/2. There's going to be a 2 that multiplies through the denominator. So I'll end up with a 1/3 as my coefficient, and then my new power on u is 3/2. If we go back to what we originally allowed u to be, u was x squared plus 3, so I'm just going to replace this u with x squared plus 3. We have 1/3 x squared plus 3 3/2 plus c. That is just the antiderivative of the first of my two terms when I'm trying to find my antiderivative, so I was able to calculate that just fine. Let's focus on calculating the second antiderivative now. Calculate the second antiderivative. It is in some ways already written where the denominator has a function in parentheses. And moreover, if I do just choose this to be u or g of x, however you want to talk about it, its derivative just ends up being 6, right? And 6 is pretty easy. You can force it to show up no matter what. I mean, technically I've got a 3 there, so I'll have to somehow figure out how the 3 dx works into the 6, but it should be manageable when all I'm dealing with is 6. So here you go. If you take a derivative, you find out that du is equal to 6 dx, or if I divide both sides by 6, that du over 6, or 1/6 du, is equal to dx. This way I can just replace this dx with 1/6 du, and go ahead and do that. Moreover, I can replace this 6x minus 1 with u, and so I go ahead and do that. Once I simplify everything, I end up with a 3/6, also known as 1/2, and then a u squared in a denominator can be rearranged as u to the minus 1/2 in a numerator. This allows me to use the power rule on u to the negative 2. Using the power rule on u to the negative 2, I'm going to add 1 to the power, and I'm also going to divide by the new power, so the power has shifted from negative 2 to negative 1, and I've also divided by negative 1. If I simplify that, I remember that u to the negative 1 power is the same as 1 divided by u, and the negative 1, the denominator is just going to give me a minus sign out front. So we're really looking at negative 1/2 times 1 over u, or in terms of my initial substitution where u was 6x minus 1, and we replace u with 6x minus 1, I have for my second antiderivative, negative 1/2 times 1 over 6x minus 1 plus c. So that's going to be the second antiderivative of the two I was attempting to compute. Turns out both of these we were able to do with substitution. The second case, I didn't really have a choice. It wasn't really a good choice of functions multiplied together, so integration by parts wasn't really on the table in the second case. So I found antiderivatives for both of them. What that means is I'm just going to add them back together when everything is said and done. So here for my overall antiderivative capital F, that's the first antiderivative I calculated, and this is the second antiderivative that I calculated. So I add the two of those together, and then to compute my final definite integral from 1 to 2, that's just me evaluating the antiderivative here at 2 and subtracting, evaluating it at 1. So if I just plug in a 2 here and here, that's this expression. If I plug in a 1 here and here, that's this expression. If I simplify both of those expressions, it looks like I've got 1/3, 7 3/2, minus 1/2 times 1/11. My c's always cancel. You can actually omit those on definite integrals if you want. I'm going to subtract 1/3 times 4 to 3/2. I'm going to add 1/2 times 1/5. Now, if this were an exam or a quiz, etc., I am more than happy with leaving the answer like this. It really doesn't need to be simplified if you're not allowed a calculator on your exams, etc. I did simplify the fractions a little bit, but not too much. But if you happen to grab a calculator and find out what this is equal to, it's approximately 3.56. You wanted to go through that work to see what it was equal to. Let's make our lives considerably harder. We didn't really need to give ourselves grace in the last problem. This problem is going to be considerably harder. So here we're going to look at the definite integral from 2 to 4, not that those numbers matter too terribly much, but the definite integral from 2 to 4 of inverse cosine 1 over root x. So here we've got a composition of functions, which normally, because we have this function inside of parentheses, normally it says, hey, this is probably a good idea to use substitution on. So if I went out of my way to say, yeah, let's make g of x 1 over root x, unfortunately its derivative, 1 over root x can be thought of as x to the negative 1/2. So its derivative is going to be what? Negative 1/2 x to the negative 3/2. That's nowhere to be found here. Of course, in terms of integration by parts, I also don't see a multiplication of functions either. So not only does substitution feel like it may not work because its derivative is definitely nowhere to be found, but I also don't have a multiplication of two functions here where I would maybe be allowed to use integration by parts. So I have to choose one, and we're just going to run with it and see what happens. So I'm going to go ahead and just make a choice, and we'll see what happens. My choice is going to be, we were in that section about non-trivial, we had a section about non-trivial u subs, and they still work. They still work sometimes. So if we just grab the function that's inside of parentheses, 1 over root x, you never know. It could, if we just go through the motions of this non-trivial u sub, it may work out for us. So we're going to do that. We're going to name 1 over root x, also known as x to the negative 1/2. We're going to call that u. And let's recall that in the non-trivial setting, we solve this for x. And in our case, we got power negative 1/2 on the one side. If I want to cancel that, I'm going to take both sides to the negative 2 power. And so that's canceling on the one side. We end up with x is equal to u to the negative 2, which tells us how to compute a dx. That's a little typo there. How to compute dx? Well, dx is going to be the derivative of u to the negative 2 times du, also known as negative 2 u to the negative 3 du. I've just used the power rule on u to the negative 2 to recover negative 2 u to the negative 3. So that's going to be dx for us, which means in my original integral, I'm going to replace every x with u to the negative 2, and I'm going to replace every dx with negative 2 u to the negative 3 du. So I'm going to go ahead and replace all those. There's a multiplication happening here that's maybe a little bit obscure between that cosine and the negative 2 u to the negative 3 term. Same down here. Negative 2 integral cosine inverse of u all over u cubed du. Now this does maybe look a little bit simpler, right? This is maybe a little more simplified. Because at least we've gotten rid of roots. Roots aren't anybody's friend when it comes to integrating. But, if we try to integrate this single integral here, if we try to integrate that, it's really not going to go very well for us. I don't know what to do when we have a cosine inverse in a numerator, u cubed in a denominator. It doesn't look like we should use integration by parts. It doesn't look like we should use u substitution. This is really a fairly foreign integral to me, which makes me think, here I say, makes me think we may have to abandon our pursuits and start back from the beginning with a new technique. So this is the case where we do need to give ourselves grace. We're going to make a wrong decision every now and then. It was a smart decision, but unfortunately it was the wrong decision. So even though we saw this 1 over root x inside of parentheses, we tried to make a nice substitution, it just didn't work out for us. Let's try something else. We could either try a new substitution, cross our fingers again, or we could say, all right, that just felt a little bit wrong doing substitution. Let's switch over to integration by parts. Is there any possible way to make integration by parts do something here? The answer is yes. We need to remember this piece by the very end of integration by parts section we had before. You can always multiply by 1. And by multiplying by 1, we all of a sudden end up with a product of functions. Okay, so now that we've got a product of functions, we're going to use this Liate? Whatever. We've got inverse trig here. We've got algebraic here. And recall, the number 1, the constant number 1, is algebraic. It comes after inverse trig, and so our inverse trig function cosine is going to be what we're going to take a derivative of, and our multiplication by 1 is going to be the function we take an integral of. So that f is going to go to capital F, antiderivative of 1 happens to be x. Cosine inverse, we're going to take a derivative of it. And to do that, we're going to need to use the chain rule. And let's just recall really quick that the derivative of cosine inverse of x just by itself is negative 1 divided by root 1 minus x squared. That's just from our derivatives table, but we'll use the chain rule on that inside term, x to the minus 1/2. So if I'm going to calculate g prime, if I take a derivative of the outside and leave the inside the same, I get negative 1 over root 1 minus, well, instead of x squared, it's whatever is on the inside squared, so x to the minus 1/2 squared. Then we multiply by the derivative of the inside. Here I'm going to use the power rule on x to the minus 1/2. That's going to give me negative 1/2 out front. X, well, 1 smaller than negative 1/2 will be negative 3/2. And then I can start simplifying this. So I've got two negative signs. They can cancel, so those are both going to cancel. I can just pull my 1/2 out front. And I think about what's going on in the denominator here really as, well, it's a square root, so I'm going to rewrite it as something to the 1/2 power, and then on the inside I have 1 minus the 2 in the power can distribute to the power of negative 1/2. I'll end up with x to the negative 1 here, because that was in square roots, that's going to be the 1/2 power. It's going to multiply by, well, x is to the negative 3/2 power, or if it's in the denominator, x cubed to the 1/2 power. And I could have written that as x to the 3/2 power in the denominator as well. The only reason I wrote it as x cubed to the 1/2 power is now both terms in the denominator have a power 1/2, which means I can combine the terms together, and in fact that would distribute this x cubed to both inside terms there. And when I distribute that x cubed, what do I end up with? Well, I've got a 1/2 up front still. I distribute the x cubed. That's going to hit the 1, and I'm just going to end up with x cubed there. But then x cubed times x to the negative 1, the exponents add together, I'll get x to the 3 minus 1, also known as x squared, This is all going to be to the 1/2 power. I can, in fact, simplify a little bit more. That's because here's an x squared term. There's really an x squared term hiding inside of x cubed, right? Because x cubed itself is x squared times x. So if I want to factor an x squared term out of both of those terms, I certainly can. That's useful because the x squared would cancel with the 1/2 power there. So if I factor out an x squared out of that denominator, it factors out just as an x, because it's x squared to the 1/2 power, and I'm left with, well, 1 copy from the x cubed and just minus 1 from the other term to the 1/2 power. So this is going to be what G prime ends up simplifying into, and it's really not too bad once you go through the work of simplification. But of course, as I always say, there's really a reason why simplification was so stressed in Algebra 2 and pre-calculus. It's because it honestly does make our lives easier in some situations. So if you feel iffy on simplifying, it's time to study up on that. It will make your life easy on some of these problems. And there I've gone through the derivation for G prime again. We ended up at the same place we just talked about, 1/2 times 1 over x times x minus 1 to the 1/2 power. And if I go through my work of integration by parts, right, my original functions f times g, I'll have the antiderivative of f, which in this case was x, g, which we'll recall was this cosine inverse of 1 over root x term, and then we've got another minus the integral of the antiderivative of f, which is still x, and then g prime, which we just calculated. So if I substitute each of those terms in, I will end up with x cosine, cosine inverse x to the minus 1/2 minus the integral of x. So these are both my capital F, x's, here's g, and then this is g prime. What's really nice about this is that, in fact, I've got an x here and I've got an x here, and they're both going to cancel. And so that second integral that I'm going to have to compute really looks like this integral, the integral of 1 over x minus 1 to the 1/2 power. And that integral is actually pretty easily integrable if I rewrite it as x minus 1 to the negative 1/2 power. It really is a power rule problem. If you want to go through the work of a quick u substitution, call u equals x minus 1, which means du would be dx, and so you, of course, can use the power rule just on u to the negative 1/2 power, and then substitute x minus 1 back in for u. So that's just going to be a substitution, and the power rule says I'm going to add 1 to the power, so negative 1/2 plus 1, I'm going to divide by the new power, negative 1/2 plus 1, then I'm going to simplify everything. My denominator is going to become 1/2. Helps out that there's a 1/2 out front, those terms can cancel, and so that integral just ends up being x minus 1 to the 1/2 power, or root x minus 1. And everything out front just came along for the ride, right? And these all stayed the same, they were already computed for me. So that is my antiderivative, and unfortunately I am not quite done yet. Why am I not done? Well, I wasn't asked to compute the antiderivative. If I go all the way back to the beginning, I was asked to compute the definite integral with the bounds 2 and 4. So now that I have my antiderivative, I can evaluate it at both 4 and 2 and take antiderivative at 4 minus the antiderivative at 2. If I evaluate at 4, that's me plugging in a 4 there, a 4 there, and a 4 here. It's going to be a 4 here, here, and here. And if I evaluate at 2, that's going to be a 2 here, a 2 here, and a 2 here. So that's this 2, that 2, and this 2. And if I simplify a little bit, I mean, I can compute the root of 4, which happens to be 2. And I can just simplify the roots a little bit. Square root of 2 minus 1 will be the square root of 1, also known as 1. And now we get to the point where we are going to compute some inverse cosine terms. And so unfortunately, we do have to jump back to our lovely unit circle. Let's recall what the definition of inverse cosine was. We're looking for these two numbers to be x values. And then the inverse cosine will end up computing whatever theta happens to be at those particular x values. Well, let's see. Let's graph a couple points on the unit circle. The first quadrant, because these are both positive x values, right? So I think we can get away with the first quadrant. Well, that first point is going to be root 3 over 2, comma 1/2. Second point, 1 over root 2, comma 1 over root 2. And the third point will be 1/2, comma root 3 over 2. And now we're looking for specific x values, right? In the first case, x value of 1/2. That shows up right here. So we're asking for the angle measurement associated to this x value. That angle measurement is going to be pi over 3. And so that's why you can see I've replaced the first case with pi over 3. In the second case, I'm looking for an x value of 1 over root 2. There's my x value of 1 over root 2. What is my angle measurement? Well, my angle measurement here happens to be pi over 4. So that's why I've replaced that cosine inverse with a pi over 4. I can simplify everything a little bit. The c's always cancel with one another. And that's the expression I get for my definite integral. If I decide to plug it into a calculator, it's approximately 1.89. That was a nice example of where we did have to give ourselves grace because we made the wrong decision right away. But it all worked out in the end after making one wrong decision. Here we are at one final case, which, once again, will test our abilities to try to make right or wrong decisions. Let's attempt to integrate the definite integral from 6 to 11 of the ratio x minus 2 over x minus 3 root 4x minus 8 plus 3. And as always, I don't like thinking about the 6 and the 11 right away. I just want to compute the antiderivative, and then I'll figure out how to evaluate at those bounds. So let's look at the antiderivative first. It's always going to be to my advantage to rewrite terms in parentheses if I can. This will make a lot of sense to put things in parentheses here as an x minus 2 times. Well, a denominator can always be written as everything the denominator in parentheses, the negative 1 power. And the square root, of course, can be parentheses as to the 1/2 power. And so now that I've written it in the following form, we do see a lot of functions in parentheses. We unfortunately also see this multiplication here. So the fact that there's multiplication makes me think maybe integration by parts is a good choice. The fact that we see not only one, but 1, 2, 3 sets of parentheses makes me think that substitution could be a good choice. So we really have to have some intuition to decide which one we're going to do in this case. Now, I do see some intuition, but I'm not going to let you in on what I actually see for intuition. I want you to pause right now and decide what you think you want to use in this case. Okay, hopefully you made a decision. As far as the book is going, we're going to go, since I see this product of functions right away, let's just choose the product of functions. There they are. And we definitely have one function which gets easier if we go ahead and take a derivative of it, right? So this x minus 2 will get quite a bit easier. If we take a derivative, the derivative of x minus 2 happens to be 1. And so that's why I'm going to label that g, in which case its derivative is 1. I'm going to label everything else in parentheses, including the negative 1 power, f, and then I have to compute its antiderivative. And now we can see why maybe integration by parts, not the world's best choice here, because how in the world am I actually going to compute that antiderivative? Did I really make my life any easier by trying to do integration by parts? No, I certainly didn't. So that's not really going to be able to be computed. We get to give ourselves grace and say, okay, I'm sorry, I made the wrong decision. Let's stop trying to do integration by parts. Let's try to do some substitution here. So now in terms of substitution, I've got quite a few parentheses here. Which function should I choose inside of parentheses? Well, I'll tell you what I have intuition to not choose, and that is kind of this outer collection of parentheses with the minus 1 power here. The reason why I would say don't choose this, because there's more parentheses inside. In some sense, we should be grabbing like kind of the smallest nested version of functions for substitution, right? Because that g of x or the u sub needs to go inside of other things. And so if these are in some sense the outside parentheses, we might as well choose the inside parentheses as the function that's going to be our substitution function. Now with that said, I actually end up choosing not the inside function at the bottom, but I end up choosing the x minus 2. Now, why would I choose the x minus 2? Here's our three possible choices of functions. Why don't I choose this 4x minus 8 to the 1/2? It's actually because it really is x minus 2 in disguise. Why is 4x minus 8 equal to x minus 2? Well, it's not. It's equal to 4 times x minus 2, right? If I distributed that 4 to x and the 4 to negative 2, I'm going to get 4x minus 8. Not only that, but 4 is actually, you can take the square root of 4. So I could rewrite this entire expression as x minus 3 times the square root of 4 times x minus 2 to the 1/2 plus 3. And root 4 is just 2, right? So that's just going to end up being 6 as the middle term there. And now you can see actually x minus 2 and x minus 2 are really both the only functions in parentheses that are left if I don't want to choose the outer parentheses. Okay, so I'm going to choose x minus 2 for my variable u. And in terms of, if I want to write it as x in terms of u, I can say x is u plus 2. This allows me to compute dx happens to be exactly du. So what I'm going to do, I'm going to replace every single copy of x with u plus 2. So that means this numerator copy of x with u plus 2, that x with u plus 2, this x with u plus 2, and replace dx with du. What does that give me if I go through and simplify? Well, the numerator, the 2's cancel. In the denominator, the 8's cancel, right? Because this 4 is going to distribute to both terms there, so the 8's cancel. And what I'm left with is a u over u minus 3 root 4 times u plus 5, or as we already saw before, that root 4 is really just a 2, so it's 3 times 2 times root u, also known as 6 root u plus 5. Okay, so how do I want to integrate this now? This may seem a little bit tricky. Well, let's think about what's actually going on in this denominator. It doesn't really look like it, but that denominator is a quadratic function. And you're thinking, Evan, what do you mean it's a quadratic function? The power is only 1. It's u to the first power. Well, yeah, but we should start to think about variables as no longer just themselves. They're all possible versions of themselves, right? They can be whatever they want to be if they believe in themselves. So we could let this u happen to be something like y squared, and that's really what I have down here. If we let u be y squared, then u to the 1/2 is actually y squared to the 1/2. It's just y. This ends up being y squared minus 6y plus 5. There, we've got ourselves a quadratic function. And so there's actually a quadratic function hiding in the denominator. But what that actually is, when I do this u to the 1/2 is equal to y, or y is equal u equals y squared, that itself is another substitution. It's a substitution that was subtle, right? It was something that we just decided to force to be in our problem because we like quadratics better than roots. And so we do that, and we say u to the 1/2 is equal to y, or u is equal to y squared, and we find out that du has to be 2y dy. So we're going to replace this du with 2y dy, and the rest of them with y squared, with y, and with y squared. Where does that leave us after we simplify this giant expression? Well, it leaves us at 2 integral y cubed over y squared minus 6y plus 5 dy. Can we integrate that? Feels like no. Well, there's a theorem that we're going to run into eventually in this course that actually says all rational functions are integrable. What is a rational function? It's a ratio of polynomials. So as long as both the numerator and the denominator are polynomials, it has to be integrable. And you may be wondering, how in the world do we actually integrate that? Who remembers our best friend, polynomial long division? I'm going to take y cubed and I'm going to divide it by y squared minus 6y plus 5. How do I get y cubed from y squared? Well, I multiply it by y. That'll give me y cubed minus 6y squared plus 5y. I'm going to cancel y cubes. I'll end up with 6y squared minus 5y. How do I get 6y squared out of y squared? Well, I'm going to need to add 6 to that. I'll have 6y squared minus 36y plus 30. And the 6y squareds cancel. I'll end up with, I'm subtracting the bottom line from the above, so I'll actually have 31y minus 30. And that's no longer divisible by a quadratic, and so this is going to be my remainder term, plus the remainder term, 31y minus 30 divided by y squared minus 6y plus 5. So here you can see this long division has given me the decomposition you see here. And at this stage, I wouldn't expect you to be able to decompose our remainder term. This is once again going to be reliant on a hint from me if I ever expect you to get this far. And the hint will be that we're going to do some partial fraction decomposition, but I will tell you that this expression is equal to the sum of these two terms. And once we find out that that expression is equal to the sum of those two terms, this ratio of functions can be fully decomposed as y plus 6 plus 125 over 4 all over y minus 5 plus negative 1/4 over y minus 1 dy. And each of these terms we know how to integrate. We have a power rule, a natural logarithm, and a natural logarithm. If I go through the power rule into natural logarithms, I have y squared plus 12y, 125 over 2 is coming along for the ride, log y minus 5, and then a negative 1/2 coming along for the ride, log y minus 1 plus c. But keep in mind, we actually went through 2 rounds of substitution here. Our second round of substitution, we decided that u to the 1/2 was going to be equal to y, or rather that y squared was equal to u. But what am I going to do? I'm going to replace every y here with u to the 1/2. I can do that. I end up here. But I also had an original substitution all the way back at the beginning. X minus 2 was equal to u. So all the way back at the beginning, each of these u's is now going to be replaced with x minus 2. And so I've got x minus 2 plus 12 root x minus 2 plus 125 over 2 log root x minus 2 minus 5 minus 1/2 log root x minus 2 minus 1 plus c. And you would think that we are done now. But unfortunately, we are not, because this problem did not ask for the antiderivative. This problem asked for a definite integral. And so our definite integral, we found our antiderivative. We need to evaluate at the bounds 11 and 6. So if I go all the way back to our antiderivative we've calculated, I need to evaluate our antiderivative here at the bounds 11 and 6. When I evaluate at 11, I'm going to plug in 11, 11, 11, and 11. Here we are. And when I evaluate at 6, I'm going to plug in 6, 6, 6, 6. Here we are. And then, you're probably exhausted at this point. You just circled that answer and tell me you did a good job. But I'm going to go ahead and simplify this a little bit. These numbers 11 and 6 were chosen well because we end up with a lot of root 9s in all of the 11 cases. We end up with root 4s in all of the 6 cases. And so we end up with log, absolute value negative 2, log 2, log absolute value negative 3, and log 1. And if we use some log rules to combine these together, we end up with 17 plus 1/2 log 1 plus 62 log 2 minus 125 over 2 log 3, or if we plug that into our calculator, about negative 8.69. Before you freak out, this last problem was supposed to be absolutely insanely hard. I'm not asking it on exams. I'm not asking it on quizzes. I want to show you just how powerful our techniques are. We can actually make it quite far with our techniques that we've learned. So very few professors will ask such a problem to be computed on exam. Maybe for a really tricky homework problem they will, and they'll help you out along the way. But I really just wanted to give us practice, intuition, show us that we do need to give ourselves grace sometimes when we go down the wrong path. Anyway, that's all I got for this chapter even. We're going to be moving on to the discrete calculus in the next chapter. I hope you like it there. See you then. Bye.